Okay, we'll go ahead and get started. What I thought we would do is just go through the first two slides of predicting the product and then showing you the sort of thought process that we'll take to make alcohols. And we'll spend a good portion of the lecture on how do we make carbon anions, add them to carbonyls. And then if there's time, we'll finish with the reverse process of a reduction, which is oxidation. So to keep in mind the reagents that we learned, sodium borohydride and lithium aluminum hydride. First thing we want to do is identify the oxidation state of our carbonyl. So here we see it's 2, it's an aldehyde. And I'm going to circle that H. So there's already an H bonded to the carbonyl carbon. We're treating with sodium borohydride, so that's a source of H minus, so it's adding a second H. So when you reduce an aldehyde, you're always going to get a primary alcohol. So you had an H on there, then you're adding the second H. You've reduced it down now from oxidation state 2 to 1, and it's a class of alcohol called primary. So if we look at the second case, we're starting with a ketone. Again, oxidation state 2, but this time we're going to use lithium aluminum hydride. If you notice the substituents bonded to the carbonyl carbon, they're both carbon. And then you're adding an H, so this has to end up as a secondary alcohol. So those are just things that you can keep in mind, what you're starting with and how to rationally predict what you're going to end up with. So just a brief recap, sodium borohydride only acts on oxidation state 2. Lithium aluminum hydride is 2 or 3. So those are, I would say those are like predict the product type reactions. Another way of thinking in organic chemistry is called retrosynthesis. And this is the design. You're given the product, what would you start with, and then what reagents would you use to carry out the forward reaction. So if we were given a secondary alcohol, what should the starting material for that be? So if we draw in that hydrogen, we see that that's the hydrogen we have to add. So again, it's oxidation state 1 in the product, so it has to be 2 in the starting material because it's going through a reduction. So we would say that this could come from this ketone. And so an appropriate reagent for that would be the sodium borohydride because it started at oxidation state 2. In the next case, we have a primary alcohol. So this could come from an aldehyde. So I'll just write ketone up here. So it could come from that using sodium borohydride. Alternatively, we could start with oxidation state 3. Say we want to use a methyl ester. And then we would have to use sodium borohydride, or excuse me, lithium aluminum hydride. If you started with either of those and you matched the reagent properly, you would still get the same product. Again, because lithium aluminum hydride is pretty reactive. What it's going to do is first do one addition of hydride to get the aldehyde. So it forms that in the reaction, and then because that oxidation state is more reactive, it's going to get further reduced down to the alcohol. So again, this was an example of you can go 3, you pass through oxidation state 2 down to 1 in the reaction. And so now moving forward, what we're going to do is look at, instead of using H- as the nucleophile, we're going to look at carbon-based anions. So those are called carbanions. And more specifically, they're called organometallic. So it's basically you have sort of like C- and then some metal M+ that's balancing off the charge. So we've learned so far these different bond types. So these are nonpolar bonds. And then where this line is, those are polar. And so we see that, carbon's delta plus, nitrogen's delta minus, delta plus, delta minus. And that's based on, sorry, that should be negative. That's based on electronegativity. So the thing with when X is that heteroatom, NOF, the carbon's always delta plus. But with a carbon anion, the carbon's going to be negative. So how do we reverse polarity? We need to take the carbon from delta plus to full minus so that it can act as a nucleophile. And so that is a carbon anion. The M is typically a metal, either in the +1 or +2 oxidation state. The carbon can be any of the hybridizations that you've learned so far, sp3, sp2, or sp. And so on the next slide or two, they're all organometallic reagents, but sometimes they're given specialized names based on the scientists that sort of discovered it, made it popular. So for the carbon hybridization, an sp3 hybridized carbon anion will start from an alkyl halide. sp2 starts from an aryl halide, so that's an aromatic ring. And then sp, you pretty much have to use a terminal alkyne. And the next slide will show you specific examples of those structures, and I'll point out the hybridization. So for the halide ones, the alkyl and aryl, typically iodide will react faster than bromide, will react faster than chloride. And then the metals are typically lithium, sodium. Potassium is sometimes used. Potassium metal, it looks sort of silvery. It's stored in mineral oil because it's pretty reactive. You take it out, if you slice it with like a butter knife, it's a metal, but you can slice it. It's pretty easy to slice. It starts off shiny, but within like a couple seconds, it starts to dull because it's so reactive, the air is oxidizing it. In magnesium, which is ends up being, so magnesium 0 goes to magnesium 2 plus. So that metal will actually hold 2 of the carbon anion ligands. The other important thing to note is these reactions must use aprotic solvents. So you cannot use any sort of functional group that has an acid, an alcohol, or an amine. So things like hexane, toluene, diethyl ether, or the cyclic ether, tetrahydrofuran. Those are solvents that you run these in because they will not interfere with the reactivity of the carbon anion. So this is a one-slide summary of how you form them according to the hybridization you're starting with. So with an alkyl halide, the carbon I'm highlighting in blue, that's sp3 hybridized. So we know bromine has 3 lone pairs, so that's delta minus, and the carbon's delta plus. If you treat that with lithium metal in hexane, essentially what is happening is that lithium 0, lithium has an electron it wants to give up. And so you use 2 equivalents of that. And a way to think about it is it's inserting into that carbon halogen bond where the carbon now gets 2 electrons and it becomes negative. So that's what I mean by that delta plus is inverting its polarity to full minus. And so that's going to be a nucleophile. That will want to attack a carbonyl group. And then the lithium bromide is a byproduct that's solid and that precipitates out of the solution. In the next example, we're using an sp2 hybridized carbon. So that's what I mean by aryl or aromatic. So again, delta minus, delta plus. This time we use magnesium. And so this is called a Grignard reagent. And you might actually do this at some point this semester. You take these magnesium turnings, they're just like little shavings. Probably, it looks like a little curl, like 2 or 3 millimeters long, but it's curved. You put it in, THF is the solvent, you then add your bromide species. And over the course of time, you'll actually see that metal disappear. And so it's kind of interesting to think that you have this organic solvent, THF, then you have this metal. They should not be soluble at all. But over time, it solubilizes and disappears. That's because it's going to insert into that bond and form this Grignard reagent. So notice now the magnesium has a Br minus ligand, and then that carbon as shown is negative. So the magnesium is overall 2 plus. And so you guys, I think you'll make that you'll do a carbonyl addition to make an alcohol at some point this semester. And then the last set here for hybridization, a terminal alkyne is when you have an sp hybridized carbon, and then you have that H. And again, that makes that H pretty acidic. I think the pK is about 15. So if you treat with a base, the base will abstract that, and that's how you get your negatively charged carbon atom. And so these are different methods for generating those based on hybridization. And then what we'll see over the next run of slides is we're going to take some of those, react them with the different classes of electrophiles. So the first class of alcohols we'll look at making is primary. And so in this exercise here, we're given the product. So we're given benzyl alcohol as the product. So that carbon has 2 hydrogens, and then that other carbon, that's what makes it primary. And this is showing you in the reverse sense of what you can make that alcohol from. So if that blue carbon, if we want that to be the negative, then this green one has to contain the carbonyl group. And so ultimately when we do that, we get back to this molecule called formaldehyde. So that's the C1 aldehyde. Does anyone work in the hospital? Do some shadowing at all? So formaldehyde is used as a preservative for cadavers. So it has a really, you'll know it when you smell it. It's super potent. And so let's look at this in the forward direction. So that's, we're kind of looking at what can be the nucleophile, what can be the electrophile, but in the forward direction, we would take that Grignard reagent, which we saw how to make on the prior slide. So the bromobenzene plus magnesium zero metal in THF, that makes our nucleophile. The formaldehyde is the electrophile. So delta minus, delta plus. We know that that carbon is minus. Put a plus charge on the magnesium. So that negative is attracted to that positive. We break that pi bond. And then what happens, so that's called a nucleophilic addition. Is that it sort of stops there until you do this last step, the workup step, where you're adding acid. So if I just abbreviate that as H+, that's how that alkoxide gets protonated. If you don't add the acid, it'll just sort of sit there forever until you adjust the pH till it ends up as the neutral compound. So as a question here, what is the molecular formula of the product when propyl magnesium chloride? So we want 3 carbons, is treated with formaldehyde, followed by acidic workup. So overall, we're starting with 3 carbons. Then the fourth one is coming from the electrophile. So this will attack there. We break the pi bond. So there's our 3 carbons. We're making a bond to the fourth, and that's going to bear the alcohol. So this would be a primary alcohol, more specifically 1-butanol. So we have 4 carbons, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. And then 1 oxygen. And so that would get us C is the correct answer. So that would be one way of making that, using a carbon anion. Another way that you could think about making this, if you took this aldehyde, so butanal, so you have all the carbon atoms in there, but now you need to reduce that oxidation state, so you could use sodium borohydride in methanol, and that would get you to the same product. And we'll see in terms of the design of things why people want to go through this exercise. You know, if you're interested in business or logistics, these are legitimate jobs that people have at pharmaceutical companies where you're sourcing reagents. You know, if you're trying to make this stuff in kilogram, multi-kilogram scale, you want to do it as cost efficient as you can based on the reagents you're starting from. So another way to make primary alcohols is to use this reagent called ethylene oxide, which is an epoxide, so 3-membered ring ether. So we know that ether epoxides are pretty reactive. You have basically ring strain. So that's a good electrophile. But now notice the difference in this primary alcohol. So I'll highlight in green. So those 2 carbons are what come from the epoxide. So if we wanted to make 2-phenylethanol, we could start from the organometallic, where the blue carbon is, again, coming from the nucleophile. It's going to attack that ring, open it up, and now you have those 2 green carbons coming from the epoxide. So the question in green there is, it's, again, a good electrophile because you want to open up that ring strain so it's not there. So that's why it's reactive. So the Grignard reagents, again, this one would come from the chlorobenzene with magnesium metal in THF. So you can use iodo, bromo, or chloro. Fluorines don't really work for this because that carbon-fluorine bond is much stronger. It's harder to make these. But once this happens, again, oxygen's delta minus. It doesn't matter which carbon in this case you attack. So this negative will attack a carbon, and then we break open the ring. we do the acidic workup, and now we have an alcohol. Just to point out, maybe I'll highlight this one in yellow. So that's the carbon bearing the alcohol. The blue carbon was the nucleophile. See the relationship between them? You have that spacer in there. So that's how you determine whether you use formaldehyde or the epoxide, is how far away things are. So this is a reverse problem. We want to make that 1-hexanol. So there's 1-hexanol. And it says we want to use ethylene oxide as the electrophile. So what this is telling us is that, again, maybe I'll just use the colors. If the yellow is going to be the carbon bearing the alcohol, then we'll use green as the other one. So those two carbons have to come from there, which means that we're actually forming C2 to C3. So the blue carbon at C3 has to be the nucleophile. So 3, 4, 5, and 6, that's 4 carbons. So we have to have a negative charge there. So with 4 carbons, it has to be a butane derivative. So the best answer would be the butyl magnesium chloride. That's going to supply the right number of carbons to make that final molecule. So the important part of all of this is, learning the versatility of what bonds you can sort of break to make something in the forward direction. Any questions so far? So we'll look at what do we need to use to make secondary alcohols? What do we need to use to make tertiary alcohols? So the thing we want to make is 1 cyclohexane, 1 all, as shown there. So that's a secondary alcohol. And the electrophile that we're going to use has to come from an aldehyde. Well, in one route. There's other ways we could do this, but so if I draw in this H, that H is telling us, yes, we can use an aldehyde to make this. So the aldehyde, again, I'll color it yellow. That's going to be the electrophile, and then the blue carbon is going to be the nucleophile. And so just to show where would we get, that nucleophile could come from, say, this cyclohexyl iodide that we treat with lithium metal and hexane. So that's how we would actually make that. Again, the choice of how you would carry this out in a lab comes down to what are the costs of the reagents. And when you're doing it on large scale, the other thing that's considered is can you get enough of it? You know, it's not like walking to Walmart. You know, I mean, when I'm talking large scales, I mean, if you're ever bored on the weekend, if you go downtown by the train station and you sit there for a couple hours, a train will eventually go by carrying chemicals. And, you know, these are like big tanker size, like the size of a semi-truck. I mean, that's the scale we're talking about. And so with that, there's safety precautions. You know, no one wants one of these trains tipping over in their backyard because then the whole city's screwed. And then ultimately toxicology. Is this stuff safe to handle? Do you need specialized equipment? I mean, can humans be around it within the OSHA permissible limits? Again, you might not be an organic chemist, you might not like this stuff, but you know, ultimately, if you're looking for a job and you have a little bit of this knowledge and you like business, people do this. And I worked in the pharmaceutical industry for a little bit, and the people that did this stuff, you get to travel a lot because you get to go see the places that make these things to ensure that they're making the right quality of starting material. They're not giving you 50% junk in your batches that you're getting. So, you know, each class you take, you'd have to specialize in something, but it opens the doors for a lot of different sort of jobs. So that was one way of making that. Another way of making it, so this was yellow, this was blue, and so there was this H in there. So that H has to belong to the aldehyde. But so we were making that bond right there. But there's also this other carbon substituent here, right? So if we make that the negative carbon, then all of this part has to be a different aldehyde. So that's a second way of doing it. So say we want to chop right there. That's going to get us one carbon. So this would be CH3 MgBr. And then everything else has to come from the aldehyde. So that would be the aldehyde to use for that partner. And so that would be a second way of doing this. So this would be methyl magnesium iodide. Again, or bromide or chloride, because that really doesn't play a part in the ultimate reactivity. So here we're starting with a C2 aldehyde. This is ethanal. We're reacting it with a C2 nucleophile. This is ethyl magnesium bromide. And the question is asking you, what's the name of the product? So this carbon is negative. It will attack that carbonyl, break that bond, and then when we work it up, way to sort of predict the right product is, I'm going to draw those two carbons. This was at oxidation state 2. It has to go down to 1 because we're adding to it. And it has to be the alcohol. So this is the bond we just formed right there. And then from that are two carbons. And so when we number this properly, we get 1, 2, 3, 4. So that would be 2 butanol. So we made the C2 to C3 bond. using those conditions. So just as a review, again, there's 2-butanol. This question is asking you how many hydrogen atoms are attached to each carbon. What do you think the best answer would be? So D is in dog. Again, the point of that is that's your how you determine your ratio in the proton NMR. So we talk about uniqueness, sets of hydrogen, then we talk about the ratio. That's what that number is, the attached hydrogens. And so let's see what you remember about now C13 shifts. So just as a brief review, on the x-axis was ppm, and that was chemical shift. And we had learned last semester that, sort of a way to think about it is methane is sort of 0. And as you start substituting H's for other things, you're pushing it, towards the end of the scale, which is at about 220 parts per million. So which carbon number is the furthest away from 0 in this molecule? Carbon 2, because that has this oxygen, so that's delta minus, that carbon's delta plus. So that carbon looks the least amount like methane, so it has to be the furthest away from 0. And so based on that, we can definitely eliminate C. You have these B and D, those numbers are sort of close. But when we scan the answers, the chemical shift of 69 parts per million is the furthest away from, what am I talking about? Sorry, let me reverse and reset. So we said C2 is the furthest away, so that's this number here. So that's where we can start analyzing the rest of them. I don't know why I was focused on C1 for whatever reason. So from there, what you're going to do is then look at the other carbons, 1, 3, and 4, see how close they are or how much they match to methane, and then if their chemical shift is like that. So let's just go through B. This CH3 group looks the most like methane, so that should be 10. 1 and 3 are both bonded to 2, so they're going to be shifted a little bit further away. 1 is a CH3, 3 is CH2, but it has 2 carbons, so that means 3 should be a little bit further away than 1 is, and so we see that in this. So 23 for carbon 1, 32 for carbon 3, just because of the additive effect. And then, the way I write these, I just sort of shuffle a number down a diagonal, and that's how you can sort of eliminate some of the other responses is distractors, I guess. Again, on your Module 2 exam, there'll be some IR, NMR data that you need to interpret. And typically what you're doing is just counting signals. Does it have the right number of carbon signals? Or given the attached hydrogens, does that ratio make sense? That's how you want to approach that. And then I think on your final, there might be 3 or 4 total NMR problems. So it's not much, but if you have that intuition, you can definitely get those right. From, I think the version that we give for Organic 2, if you just count the signals, you can, it doesn't matter if you know the reaction, you'll get the answer right just by counting. And so now the tertiary, there's kind of 2 things I want to point out with tertiary. There's one sort of special case, and then there's the generalized case of any tertiary alcohol. So let me highlight this carbon here in red. We said that was the carbon bearing the OH was the carbonyl carbon. And this is the special case because when you look at it, 2 of the substituents are the same. And really what that is ultimately telling us is that we can start from an ester that's at oxidation state 3, and you're adding that same reagent twice. So you're just using an excess of it. And the reason that happens, when you add the first reagent, it does an addition, and then it eliminates off that part of the molecule. So it forms a ketone, which is now at oxidation state 2, and then that adds another equivalent of that carbon anion to give you your alcohol. So that the spot, what you're looking for is, again, if 2 of the substituents are the same. So we call that a double addition. And so in this problem, so what do we start with when we look at the tertiary alcohol here? 2 of the substituents are the same. They're coming from this methyl magnesium bromide. So right here and right here. So we need to start with one of these cyclic esters. So again, they're all oxidation state 3. And a cyclic ester is called a lactone. So what's unique about this is once it does that first addition, and then it eliminates, I'll just highlight in blue. See this oxygen in blue? It's coming from that oxygen. So what we have to determine is which one of those rings, what size ring is going to give us that starting material. So maybe I'll highlight in blue, or no, I think we're using yellow for the electrophile. And so we'll count from that yellow dot down to that highlighted, blue highlighted oxygen. So based on that counting, what do you think is the correct answer? Huh. B. So B is the correct answer. So if you look at carbons 2, 3, and 4, they're all CH2 groups. So again, that number was the oxidation state, but carbons 2, 3, and 4, they're still coming along for the ride. Nothing happens to them. And that blue highlighted oxygen ends up there. So esters, whether they're acyclic or cyclic, if you see the same substituent, it's been added twice. Any questions? So here's a summary of all of that. If you start with an aldehyde, you end up with a secondary alcohol. A ketone, tertiary, again, this is for addition of organometallics. So the ketone already has 2 carbon substituents. You're adding a 3rd carbon substituent, so it's tertiary. If you use a carboxylic acid and you try to add to it, say you have this, and you're treating it with, this 3-carbon carbanion, the only thing that's going to do is an acid-base reaction. It's not going to do an addition. So you'll end up with minus Li plus, and then your byproduct would be propane gas. So carboxylic acids are not good substrates for these additions. Esters will give you tertiary, and acid chlorides, which are the same oxidation state as an ester, they'll still give you tertiary as well. And so over the next couple slides here before we finish up, we're going to look at a specific compound and sort of analyze it. How are all the different ways we can make it? What are the pairs of nucleophile with electrophile? So notice here, so we have R1, R2, R3, and really what we're going to focus on is this down here is a model substrate, so there would be R1. This would be R2, and then that would be R3. And we're just going to fill in the table of how can we analyze this to set up these pairs of electrophiles that contain the carbonyl, and then nucleophiles that come from the organometallic. So really the key thing is identifying, the carbon bearing the oxygen, and then you're basically going to, for a tertiary alcohol, going to make a ketone out of it 3 different ways. So as a recap, again, just to review, is that carbon stereogenic? So we would say that's true. So that means it has 4 different substituents. You have a phenyl ring, an ethyl group, a methyl group, and then an OH group. So again, if this is our product, with this indicated pair, this would be, the aldehyde would be your electrophile, the ethyl magnesium bromide would be your nucleophile. If you reacted these two together, would you get that product? So the answer here would be false. And so the reason is, if you react these two together, you're going to end up with a secondary alcohol. Again, it's the presence of that H that makes it secondary. So if you used methyl magnesium bromide, so that's CH3, MgBr as your nucleophile, it says what would the name of the electrophile be? So maybe let me back up there. What major functional group would the electrophile have in terms of just a carbonyl containing functional group? So if this highlighted blue CH3 ends up being that, this whole rest of the molecule has to come from the electrophile. And since this is at oxidation state 1, that means the electrophile has to be at oxidation state 2. So that carbon has to be at 2, and so that would be the starting material for this. And a common name for this is ethyl phenyl ketone. So that's one way of doing it. There's essentially, for any alcohol, there's 3 ways. So we'll look at the other 2. And so now flipping it a little bit, it says if acetophenone. So acetophenone is basically methyl phenyl ketone. So if you're using that as your electrophile, how many carbons must the nucleophile contain? So we basically want to make that bond, so it must contain those 2 carbons, which would come from ethyl, CH3, CH2, MgCl, so ethyl magnesium chloride. So that would be strategy number 2. And then you can see where this is going. Strategy number 3 says we're going to use phenyl lithium as the nucleophile. So that's phenyl lithium. So we would then need those 4 carbons as the electrophile. And then that's 4 carbon ketone, so this is called butanone. And so overall, you can make any alcohol 3 different ways, basically. So here's a summary of those 3 pairs. And again, it's like, we call these routes. And practically speaking, when you're determining a route, it's like if you want to go from here to New Orleans, if you have Apple Maps, it's going to give you like 2 or 3 ways, right? So that's like a route, which is the most time efficient, which avoids tolls, that sort of thing. Is there a Buc-ee's on the way that you want to stop at? So that sort of thing. There's a student in my research group. His family owned like some condo or something down in Orange Beach, so he would always stop at that Buc-ee's on the way down there in Alabama. And he would always rave about how clean the bathrooms were.
The bathrooms are so nice in Buc-ee's. I have been to like every single gas station.
Yes.
From like
Those are pretty nice.
from like Pascagoula to Orange Beach. Buc-ee's is always the best.
You know why they're nice? Because they pay extraordinarily well.
They
$15 an
pay
hour at
really
least. I was like, that's the
well.
minimum.
The manager there makes like over 100,000, right?
And they
So, I mean,
have,
it's-
and they have
Yes.
the means.
So, there you go.
The manager at the one in Alabama makes, I think, like over $200,000. He's been there for so long.
Yeah, he's not giving that job up no time soon. But I mean, also, it's like with that salary comes a lot of responsibility, right? I mean,
Kind of. He's kind of like an online manager who just kind of manages their times and bookings.
Yeah.
But you have to be on your A game there. Like
Right.
if you mess up once, you're out.
right?
Like,
Yeah, it's cutthroat. So that's again, just ways of thinking about these things. Again, if you're trying to make a lot of this and something's not available, what's your plan B, your plan C? So here is, just talking about logistics and considerations for that, how this is practically done on like very large scale. So questions before we transition into the sort of next topic for alcohols. So that was how we make alcohols from carbonyls. Now we're going to do the reverse process. We're going to oxidize them. And the general mechanism for oxidation, it's pretty much the same no matter what reagent you're using. To sort of help you out, you absolutely must start with a primary or a secondary alcohol. This does not work for tertiary alcohols. So if you spot a tertiary alcohol, you cannot oxidize it. The reason for that is, again, if the carbon bearing the OH group is the carbonyl carbon, it has to have at least one oxygen, and then being an alcohol, the oxygen itself already has, the carbon has to have one hydrogen, the oxygen already has a hydrogen. So a way of thinking about oxidation is the loss of H2 across that bond. So the carbon and the oxygen are both losing an H. That's an equivalent of H2, so it's overall oxidation. And essentially what happens when I say here activation of hydroxyl group, what that means is, what reagent are you using? Because the mechanism's the same. It's going to take that H, which I've circled in green, and it's going to transform it into a leaving group. And at that point, this is just what you learned from Organic 1. It's an E2 reaction. You have a base that comes along, it abstracts that hydrogen, and it does an elimination to form the pi bond. And again, there's, like trends. So a primary alcohol will always go to an aldehyde. A secondary will go to a ketone. So I'm gonna put an asterisk by aldehyde. So that's an oxidation because it's going from oxidation state 1 to 2. Aldehydes, because they still have that H left on the carbon, they can be further oxidized up to carboxylic acids. And again, the main thing as we get into the weeds here with this is knowing your reagents. And as I mentioned before, since you take your exams on zip grade, and you can use your notes, your books, you can look stuff up. But ultimately, you want to prepare yourself for the final so that when you do see those things, you have an idea of what context they're reacting in. So to summarize the oxidation state ladder, as I'm calling it, again, you can look at any carbon atom and just count the bonds to a heteroatom. At oxidation state 0, that's your alkane. And I'll sort of highlight in blue. So a carbon, and just keep in mind that that blue is not oxygen, it's a carbon that's being oxidized up. So for an alkane, when it's oxidized in one step, it becomes an alcohol. So primary alcohol, you can go to oxidation state 2, it's now an aldehyde, and this is the special case for aldehydes only. They can go up even further to carboxylic acids, and again, that's dependent upon the reagent. Now, if we look at a carbon in the middle, so we have propane, we can go to a secondary alcohol, and then that gets oxidized up to a ketone, and it can't go any further. And then we said for this tertiary case, you can take an alkane to a tertiary alcohol, but it can't be oxidized beyond that because that carbon no longer has any H's to abstract. That's the important thing. So really you're looking for primary and secondary. Tertiaries will not react. They can't be oxidized. So my strategy for this type of problem, so it says can't, is always to draw out the structure from the name. And so those are the structures. The next thing we do is classify them. So tertiary alcohol, secondary, primary, secondary, and we'll find that A is the correct answer. And we don't really even need to know what the reagents are at this point, but if we said, okay, if 2-butanol was to be oxidized, and I'll just square bracket O, if it starts at oxidation state 1, it can only go up to 2, so that's a ketone. Sort of same thing for answer D, that has to become a ketone as well. So the primary ones are the weird ones because it is dependent upon conditions whether you end up with the aldehyde or the acid. And just to highlight that, see that H right there, still bonded to that carbon. that can be eliminated and the carbon then oxidized up to state 3. So we'll put those numbers into so our last couple minutes here, we'll finish off with what are the reagents that will do this. So specifically, we'll limit primary alcohols only going to aldehydes at this point. And no matter what, secondary can only go to a ketone. So the reagent names are PCC, the Swern oxidation, or Des-Martin periodinane. PCC is a reagent, pyridinium chlorochromate. You'll see the structure on the next slide. Swern oxidation and Des-Martin periodinane. Those are the names of the people that discovered those conditions. And so there's stuff in there rather than referring to the specific reagent. So PCC, that's not PCP. So you're not going to go lift up a car and start a trash can on fire. Is pyridinium chlorochromate. So it has this structure here. Pyridinium is a pyridine ring that's positively charged, and the chlorochromate is sort of the active species. And I'm not going to go, you don't need to know too much about the mechanism, but again, it takes that H from the oxygen, it activates it so you can do the elimination. So really what you need to pay attention to is it's a primary alcohol, so it has to end up as an aldehyde. So again, there's 2 H's. One of those H's gets eliminated. So pyridinium chlorochromate, I think, is like a red, brown solid. You dissolve it in dichloromethane, and you just use room temperature. They're pretty smooth reactions, but if you've heard of Aaron Brockovich, that movie, it is about chromium waste in the municipality she lived in. Chromium's pretty bad. It's bad because notice the valence here. So it's way beyond your normal octet, right? And so it's a toxic metal. I mean, and you know, sort of once it's in the environment, it's hard to get out, because if it's in soil, like think of mud. How do you get something out of mud? They're nice reagents in terms of synthetic efficiency. The yields are really good. So the reason that all these other reagents exist is because chromium's pretty bad to use, and obviously you can't use tons of chromium on a pharmaceutical scale because it generates too much waste byproduct, and that cuts into profit. So one alternative is what's called the Swern oxidation, and so Swern was at Temple University in Philadelphia. And so this is what's called like a witch's brew of reagents. You take these 2 reagents here and dichloromethane. You have to use colder temperature, but what it generates is this is the activating agent. Again, it transforms that H into a good leaving group. That hydrogen gets eliminated. So oxidation state 1 to 2, so you end up with a ketone. So again, I don't want to overly burden you with specific mechanisms that happen with these different oxidations. So you just sort of have to make the association of SWERN has, those sets of conditions. That's called oxalyl chloride. And DMSO is dimethyl sulfoxide. So those things react and they make this activating agent. And then we'll finish up with the Des-Martin periodinane. So they were at Illinois, and they developed this reagent. It's a hypervalent iodine called a periodinane. And again, all it's doing is activating the H of the alcohol. It's pretty mild. You can do it at room temperature. The byproduct sort of falls out of solution. You filter it away. And in this case, since we're starting with a primary alcohol, we end up with an aldehyde. So of those three conditions, the DMP, Des-Martin periodinane, is probably the easiest to run. You throw that reagent in. As time goes on, the byproduct separates out. That's how you know it's done. And then you just filter it off. And you don't have to worry about chromium, which is a mess. But we'll go ahead and stop there. And so don't forget to take your quiz. And then what we're going to do next time is, now that we know how to make alcohols, how to oxidize them, we'll look at some more reactions of them. And then we'll start with ethers and thioethers.